let's introduce now the concept of sets that are open relative to other sets that behave as the framework. So what do we mean here? To know what this notion means, first, let us recap what does the notion of open mean. So let's say we have, as usual, a metric space, X, and let's say we have a subset E, okay, that is open. That means that for every point P in E, there is some number R positive, such that, let me say it with words, then we write it with a formula. For every point in X that is within distance R from P, okay, this will be for Q in X, then Q must be in E. Okay, this is, let me write it more carefully, such that for every Q in X such that the distance from P is less than R, then Q must be an element of E. Okay, this is what being open means. Okay, so basically, that means that for every point there is some radius, and every point that is within that given radius from P, that would be, P would be the center of the neighborhood, then the whole neighborhood is contained in E. Okay, so that's what being open means. But here's the thing. So we could consider, if we want, a subset Y of the metric space X, okay? And this would also be a metric space itself, okay? Any subset of a metric space is also a metric space. Basically, you can forget about the rest of the space. Okay, let's think about this for a moment. What makes a metric space? So it's a space where a metric has been defined. So if the metric has been defined for the whole of X, for sure, it's also defined for Y, okay? So then any subset Y is also a metric space. All right, but then here's when the notion of open relative to comes in. So we could see what does it mean that the set is open relative to Y. Okay. So you see here, we say relative because we have two frameworks now, the framework of Y and the framework of X, the bigger framework, okay? So depending what is the framework we are using, things we may get different answers. Let me tell you, before we get into any more details, let me give an example of what we should have in mind. Let's say we have the real numbers as our metric space X. Okay, and let's say, to keep things simple, that Y is the interval, the closed interval 0, 1. Okay. Now, let's look at the half open interval 1/2, 1. I guess some people will look at this interval and think it's half closed, but anyway, So is this set E open or closed, or what's happening with this? Okay. So you may be thinking that's neither open nor closed because it's half-half, right? But that is relative to X, to the set of real numbers. So here we have our Y, and let's use a different color for our set E. Then this subset E, okay, that we have here, the 1/2 one, may seem at first as it's not an open set, because we can think, hey, there are points arbitrarily close to 1 that are not in E. So 1 is actually a boundary point. Okay, fair enough. But these points that we are thinking of, those are points that are not points of Y. Okay, those points are outside. We have forgotten about those. Those don't exist anymore. Now, when that happens, we need to be careful how we write things. Then we say that E is open relative to Y. Okay, because if we say that the interval, the open closed interval 1/2 1 closed on the right is open, people will freak out. Okay, so we need to be very precise, saying relative to what? Because there may be sets that are open relative to a set, but not open relative to the ambient space. Okay. Let me give another example just to close this. So let's say this. Let's say now, let's look at the interval 0, 1. Okay, if I look at the interval 0, 1, and I look at it like inside the real line, it's going to be open. No discussion about that. But now if I look at that same interval 0, 1, okay, but I look at it as a subset of R2, the plane, then we have a problem. Okay, because in this case, we should write it as X, the points X0, such that X is in between 0 and 1. Okay, but what happens here? Now, when we are looking at 0, 1 inside R, the neighborhoods are going to be intervals. Okay, but when we go to R2, our neighborhoods are balls, disks. Okay, no matter how I do it, whenever I center a disk in the segment, I will always touch points that are outside of the segment. Okay, so no point. This set E is not going to be open when I look at it relative to R2. Okay, in fact, it's closed. It's because all the points in the segment are boundary points. Okay, so we need to be careful with that. Now, this may look a little messy, but there is a way to actually see when a set is open relative to another set that is quite easy. So theorem, let's suppose that we have Y a subset of X as before. Let's say that we have a subset E of Y. Okay, so this E of Y is open relative to y, if and only if, and here comes the nice thing, I can write E as the intersection of y with an open set of x. Okay, so for some g, let me write for some open subset g of x. There we go. Okay, so going back to the example, so we said that the set E, that is 1/2 1 closed on the right, we said it was open relative to 0, 1. And that is true because this is 0, 1, which was our y, intersection, let's say, with 1/2 3/2, okay, which is, this is our g that is open in x equals r, okay? So yeah, we can apply the theorem and say, yes, it's open relative to y, okay? In case anybody wants to see the definition written, let's write it down carefully. So E is open relative to y, okay? If to each P in E, there is associated, let's say, an R bigger than 0, such that, that's the radius for a neighborhood, such that Q is in E whenever the distance between P and Q is less than R and Q belongs to Y. Okay, so this would be the definition of being open relative to Y. Okay, and now we can prove the theorem. Now to prove the theorem, so it's an only if. Remember when we have an if and only if proof, we need to show both directions. Okay, so let's start right to left. So here, if we have that G is open in X, and we have that E is the intersection of G and Y, this is what was written on the right. Then what can we say? Then we can say that for every P in E, okay, for every P in E, there exists a neighborhood VP. Okay, this is a neighborhood such that VP intersection with G, sorry, I said G, I mean Y, with Y, is G intersected with Y. What did I do here? I just took the definition of neighborhood and intersected both sides with Y. And I did this because G intersection with Y is equal to E. Okay, so this way I can say that VP intersection with Y is contained in E, and that gives me the relative neighborhood that we have in the definition. Okay, so this means by the definition that E is open relative to Y. Okay, and that finishes the first half of the theorem. Now the second half, we need to go from left to right. Okay, so here, suppose that E is open relative to Y. Okay, and let's say For all p, well, then for all p, that is in E, there exists Rp such that dpq, the distance from P to Q, is less than Rp. For Q in Y, that means that necessarily Q must be in E. Okay, this will be more clear with a picture. Let's keep things simple, and of course we are thinking more general because this is a metric space, but the easiest way to understand is with intervals. Okay, so let's say this is our E, and we have here our point P. So this is our Y. Okay, and here we have our E. All right. But now, what is the RP? The RP is this distance here. Okay, is the any distance that we can take such that any point that is in Y, that is within a distance RP from P, is also in E. Let's see. So this is P. So all the points that are to the left and inside of E, those for sure are within a distance less than RP. But if I go to the right, also I can go all the way to the end of the interval, and these points are points in Y that are within a distance less than Rp from P. Okay, so and these points are also in E. So yeah, you see how this is a little different. It's a little asymmetric. Okay, it's a little different from what we are used to. But now the way we are going to work, you saw that in the example before. I said, well, we could take the set G that is 1/2 to 3/2 open set and intersect it. I just picked one. So here, what we need to do next is to choose some neighborhood in the larger ambience space. Okay. So what I'm going to do, I'm going to double to the outside of the set Y. Okay, and I'm going to bring this distance Rp to the other side, and I'm going to just take the that neighborhood. Okay, and I'm going to call it Vp, the set of points Q in X. Here comes the thing. Okay, notice that before I had Y, now I have X. That's the key. The distance from P to Q is less than Rp. Okay, you see what happens? It's the same formula, but now because we are in X, it's a symmetric interval, if you want, in this picture that we are drawing. Okay, remember we are working in a metric space, but we are thinking about it as if we were working in R. Okay, and this is what we need. Okay, once we have our VPs, then we can define G. Okay, so remember the theorem says that there is some G. Okay, and things happen. So we need to figure out this G. So we have been able for every point to define this neighborhood VP, but you could say, hey, what happens if you shift the point? You go from P to somewhere else. And then we would need, okay, let me make this independent of the point by taking all possible choices at once. Let me take the union of all these VP that I can construct for every P in E. And then all of them are included and I'm fine. Okay, but notice here what happens. VP is open in X because we constructed it as a neighborhood in X, okay? But the union of open is open, okay? This is open in X. This is we saw the theorem that the union of open sets is open. So no need to prove that. So this G, that is the union of the VPs, is open. And now the only thing that is left is to show that for this G in particular, E equals the intersection of Y and G. Because if it doesn't, we are not proving the theorem, okay? Now, these are sets, so I need to do it in 2 steps, the 2 inclusions, right? First, that E is a subset of Y intersection G, and then that Y intersection G is a subset of E. Let's take P, P in E, and then we know that P is in VP. This is by construction, okay? Because we have built VP around P. So for sure, P is in VP. And then VP is contained in G, okay, by definition. All right. So once we know this, then it comes what I was saying, that E is a subset of Y. That means that P is in Y and P is in G. So that means that that P is in Y intersection G. Okay. So that proves the first part. We started saying P is in E. We conclude that P is in the intersection of Y and G. All right. And then to finish the proof, let's do the reverse inclusion. So here, what we realize is that VP intersection with Y, this is contained in E for all P by construction. Okay, remember what we did. What we did was to construct VP, taking the piece that was inside of E, okay, and then extending it outside. Okay, so yeah, of course, the intersection with Y is in it. And once we have this, well, because VP is contained in G, we have that G intersection with Y is contained in E as desired. And this finishes the proof.